This route finder returns a tour costing 29. But the same 5-city graph contains a tour costing 8. The strange part is that every next move looked sensible. Each time, the algorithm chose the cheapest city it could see. The damage was waiting at the very end. The task is the traveling salesman problem. Visit every city exactly once, then return to where you started. Our algorithm uses the simplest possible heuristic. Start at A, look only at the unvisited cities, and take the cheapest edge from the city you are standing in. Mark that city visited and repeat. This is nearest neighbor. It is fast, and it always gives a valid tour when the graph is complete. It does not promise the best tour. Here is the deliberately small weighted graph. From A, the cheapest unvisited city is E at cost 1. From E, B is also 1. So the route now reads A, E, B, and the algorithm has spent only 2 units. That feels like progress. But the remaining cities, C and D, are not just destinations. They're also the pieces that must leave us a cheap way home. From B, the cheapest remaining move is C at cost 6. From C, D costs 1. Now every city has been visited. The algorithm has no choice left. It must close the loop from D back to A, and that edge costs 20. Add the edges, 1 plus 1 plus 6 plus 1 plus 20. The result is 29. The algorithm did not make an illegal move. It simply postponed the round-trip obligation until there was nothing left to choose. Now stop choosing one edge at a time and compare complete tours. This order is valid. A to B costs 3, B to E costs 1, E to D costs 1, D to C costs 1, and C back to a cost 2. 3 plus 1 plus 1 plus 1 plus 2 is 8. The local rule was never told to preserve a good ending, so it spent its cheap connections on the beginning of the route. The failure is not that nearest neighbor cannot see distances. It sees the next edge perfectly. The missing quantity is the cost of the unfinished route. Which cities are still outside the tour, and what will the final return cost after we use this edge? MIT's planar construction shows the same shape even with points in the plane. A greedy tour can walk a square's perimeter first, then make a second pass for corner points. The local edge is cheap. The completed route is not. There is a practical repair that does not pretend to solve every TSP. Start the nearest neighbor run from every city and keep the best seed. On this graph, the best seed costs 12. Then make 1 2-opt exchange. In the 12-cost cycle, remove B to C, costing 6, and E to A, costing 1. Add B to E, costing 1, and C to A, costing 2. The edge budget falls by 4 from 12 to 8, and the route becomes the optimum we just checked. So use nearest neighbor as a seed, not as a certificate. Compare complete tours, try multiple starts, and apply bounded improvements such as 2-opt. Then keep the caveat visible. This 5-city matrix is a weighted graph construction, not a universal performance guarantee. Published analysis still finds logarithmic worst cases for nearest neighbor, while metric examples can approach a factor of 2. A locally best edge is evidence about one step. The route is judged only when the loop is complete.